Okay. Can you see my slides?
Yes. So
Okay.
I would like to ask the participant to close their microphones. Yes, thank you. And so Katharina Müller from Laval University, Canada, is going to deliver her talk entitled "The minus part of the class number for p equals 2 and its properties." So thank you very much, Katharina. You can start.
Thank you very much for the opportunity to speak here and to organize this nice conference. So I will give a short outline of my talk. I will first recall some definitions and preliminaries and how minus parts are defined for odd primes. Then I will talk a little bit about the capitulation problem, and in the end, I will present some results on Iwasawa invariance and explicit computations. So let me start with my general setup. I will always consider K to be a number field, and P will be any prime. It could be 2, it could be odd. And I consider the field K tilde, which is the union of all the fields K adjoint mu P to the n. So mu P to the n is a P to the nth root of unity. And as all these fields are contained in each other, K tilde is a field again. And of course, K tilde over K is Galois. And we can describe its Galois group quite explicitly. It's isomorphic to a copy of the periodic integers times W, where W is a finite abelian group. And its order either divides p minus 1 if p is odd, or the order divides 2 if p is equal to 2. And I can define K infinity to be the fixed field of K tilde under this W. Then by the main theorem of Galois theory, the Galois group of K infinity over K will be isomorphic to the periodic integers. And if I define Q to be 2 times P, then we obtain the following diagram of fields. So downstairs I have my field K. I started with, I have K adjoint mu Q. So this is a finite abelian extension, and its Galois group will be isomorphic to this W above here. I have my ZP extensions K infinity and K tilde. And as the Galois group of K infinity over K is isomorphic to the periodic integers, I have unique subfields of degree P to the n over K. So if I look at Kn minus 1, it will have degree P to the n minus 1 over K. And each intermediate step from Kn to Kn minus 1 will have degree P. And all these horizontal lines here are Galois extensions with Galois group W. And let me briefly recall what a CM field is. So we call a number field K CM if it's an imaginary quadratic extension of a total real field K plus. And in this case, the non-trivial element of the Galois group K over K plus is a complex conjugation under every possible embedding of K into the complex integers. And the cyclotomic ZP extension of a total real field is again totally real. So we have the following diagram of fields. So I take my CM field K, I take the totally real subfield, and now all the horizontal lines are Galois, and the Galois group is generated by complex conjugation. And again, I have these unique subfields of degree P to the n over K plus and K respectively. So now we can define plus and minus part. So for the rest of this talk, every field K will be a CM field. And I denote by an the P0 class group of Kn. Then an is a finite ZP module. It's not only finitely generated, but it's also finite. And for odd P, I define an plus to be 1 plus j times an, and an minus as 1 minus j times an. And the nice thing for odd P is if I take a class in an and P is odd, then this element A has odd order. So I can find a B in an such that 2b is equal to A. And I obtain a decomposition. A is equal to 1 plus j times B plus 1 minus j times B. So in this case, an is the sum of an plus and an minus, and this is even a direct sum, because if you look at the definition of an plus, complex conjugation acts trivially. And if I look at an minus, complex conjugation acts as multiplication by -1. So these two groups cannot intersect. And as I can write every a as an element from an plus an element from an minus, I get this direct decomposition. And you can also describe an plus and an minus differently by saying an minus is the set of all ideal classes such that J acts as -1, and an plus is the +1 eigenspace. And if Kn plus is the maximal total subfield of Kn, then An plus is isomorphic to An of Kn plus via restriction. And this uses the fact that the extension Kn over Kn plus is always ramified at all infinite primes. So I gave a nice definition with nice properties for odd p. So the question is, what do I do for p equal to 2? And this problem was addressed very early on. So there's a definition I will call the classical one. So for p equal to 2, I define an minus as the -1 eigenspace of J and an plus as A of Kn plus. And if we go back to p odd, we see that the definitions are equivalent, right? Because if we define an minus in this manner, we saw that an minus is the -1 eigenspace, and we also saw that an plus is isomorphic to an of Kn plus. So we have a definition for p equal to 2 that, if we extend it to odd primes, gives us what we just discussed. And the problem with this definition is we don't have a direct decomposition as in the case p bigger than 2, because for odd primes p, I could find a b such that 2b is equal to a, but for p equal to 2, this is not always possible. But we still have an exact sequence, 0 to an minus to an plus to 0. And recall for odd primes p, we wrote an as a direct sum of these two terms. So this exact sequence also appears for odd p. And the plus and minus eigenspaces intersect in an minus 2 torsion. So if I have an element in the -1 eigenspace of order 2, it automatically lies in the +1 eigenspace as well. So now I have all my basic definitions into place, and I can start to describe the capitulation problem. Of course, I have a natural injection of fields from Kn to Kn plus 1. And this induces an injection of the group of fractional ideals I of Kn to I of Kn plus 1, and on the principal ideals P of Kn to P of Kn plus 1. So I get the following diagram. I have my two injections on fractional and principal ideals. And of course, this induces a map on class groups and also a map on P class groups. So note that the rows in this diagram are not exact, because here I only look at the P part of the class group and not the whole class group. So a natural question we could ask ourselves now is, okay, we know that the embedding on principal ideals and fractional ideals are injective. So what do we know about the kernel if I look at the P part of the class group? And there's a solution to this problem. It's originally the idea goes back to Iwasawa, but I learned about the proof in Washington's book on cyclotomic fields. So if P is an odd prime, then iota is injective at least on an minus. An plus is way more difficult, but on an minus it's injective. And the problem is not only that the proof of Iwasawa Washington does not work for odd p, simply the claim is not true for odd p. So let's look at an example. If we take K to be the field obtained by adjoining the square root of -1 and the square root of 10 to Q, then the first step of the 2 cyclotomic ZP extension is just K adjoins square root of 2. So I can look at an ideal A generated by the square root of 10 and 5. And we easily see that if I act with complex conjugation on A, I get back the same ideal, because both generators are real, and A squared is the principal ideal generated by 5. So the ideal class of A belongs indeed to A minus. But if I lift this ideal to K1, these two elements, the square root of 10 and 5, have a common divisor, which is the square root of 5. So this is indeed a capitulated class which lies in the kernel of iota. So if I want to have some injectivity for p equal to 2, I have to change the definition of A and minus. And to do that, we make the following alternative definition. We say that an ideal is real if JA is equal to A. So I don't only assume that the ideal class as a class is fixed by complex conjugation, but the ideal itself is fixed by complex conjugation. And then I define AM plus as the subgroup of all ideal classes in AN, such that A contains a real ideal. So each of these classes should have a representative ideal A that is real. And then I define AN minus as the quotient of AN over AM plus. And this definition might seem a little bit arbitrary, so let me explain why we use this definition. If one considers capitulation in the classical definition, so in the one where we defined AN minus as the -1 eigenspace, then one obtains that the kernel of iota lies inside the new AM plus. So if I have an ideal class in the -1 eigenspace that capitulates from level n to level n plus 1, then this ideal class contains a real ideal. So I'm somehow defining AN minus as the quotient of AN, and I quotient out by all ideals that could possibly generate problems for me. If P is odd, this definition is equivalent to the classical one, because recall that we showed that AM plus for odd P was isomorphic to 1 plus J times AN. But if I multiply with 1 plus J, I always will get a real representative. And AN minus is a quotient now. So it was only a subgroup before, but now it's a quotient. So I can even assign a class field to it over K if I want to. And then we can prove the following theorem. If we assume that the 2 times P's roots of unity are in K, then iota is injective on AN minus in the new definition, meaning that AN minus is this quotient, and this holds for all primes P. And let me briefly explain the proof. So I will write down the proof, including all primes, but that's not really necessary because for odd P, we know that the definition is equivalent to the classical one, and we already have the theorem by Washington and Iwasawa. So let us start. So we want to show that a certain kernel is injective. So let us start with an element A times AM plus that lies in the kernel of this lifting map iota. And as AM minus is a quotient now, I have to write every element of this form. And then I can take any ideal in A. And as this class lies in the kernel of iota, I know that the lift of A times C for some real ideal C is principal in Km plus 1. And I can take a generator of the Galois group Km plus 1 over Kn and look at the element alpha over alpha bar to the sigma minus 1. And if I look at the fractional ideal generated by this thing, I see that taking alpha over alpha bar kills the C here because C was supposed to be real. And the sigma minus 1 kills the iota of alpha. So this element, alpha over alpha bar to the sigma minus 1, is a unit. But also its absolute value is 1. So it is a root of unity because I'm working in a CM field. And if I take the norm, the algebraic norm to Kn, the norm is 1. But now we can compute group homologies for these CM fields. And we can actually show that I have a root of unity of norm 1, and then there's another root of unity nu, such that nu to the sigma minus 1 is this alpha over alpha bar to the sigma minus 1. So the two elements, alpha over alpha bar and nu, differ by an element annihilated by sigma minus 1, which is in Kn. So I get a gamma, which is my generator alpha over alpha bar, and I multiply with some root of unity. Now, if we look at gamma again, the absolute value of gamma is 1. So I can write 1 plus gamma equal to gamma times 1 plus gamma bar. And as gamma is in Kn, so is gamma bar, and so is 1 plus gamma bar and 1 plus gamma. So as ideals, the ideal A and the ideal 1 plus gamma differ by a real ideal. But now A was an ideal for Kn, and 1 plus gamma is an element of Kn. So what we see is that already on level Kn, I have an equation of this form. So indeed, A times Am plus is just the trivial class. And we showed that iota is injective. And let me explain one simple consequence of this result. I take a topological generator of my Galois group K infinity of K, and I set T to be tau minus 1. And then I have an isomorphism from the power series ring in one variable T with coefficients in ZP, and I will call this thing lambda, to the completed group ring of my Galois group. And this isomorphism, it's non-canonical. It depends on the choice of the topological generator, but we don't care about this. We just fix one generator once and for all and work with it. And of course, the Galois group K infinity over K acts on each AN. So it also acts on the projective limit. And then we can adapt a proof of Washington to show that the projective limit A infinity minus, which is just the projective limit over n of AN minus, does not contain a finite subintegral. And this proof is more or less one-to-one the proof of Washington. The only difference is that now we have this capitulation freeness result for all P and not only for odd P. And this result was well known for P at least 3. And why is it interesting? It's interesting because if we do not have a finite submodule, it's somehow easy to describe AN minus explicitly using an asymptotic formula for its size. And that's what we will do later. But first, we have to introduce Iwasawa invariance. So we call a finitely generated lambda module E elementary if it is of the following form. So it consists of a finite number of copies of the whole ring lambda, finite number of copies of lambda over some power of P, plus a finite number of copies of lambda over fj to the dj, where fj are irreducible distinguished polynomials. And let me briefly recall what a distinguished polynomial is. So we call a polynomial distinguished if all its coefficients are divisible by P except for the leading one. And if M is a finitely generated lambda module, and then exists a unique elementary lambda module E such that E and M are pseudo-isomorphic. So what does pseudo-isomorphic mean? It means that we have an exact sequence of lambda modules, 0 to K1 to M to E and to K2, and K1 and K2 are supposed to be finite. And we call S the rank of M. We define mu to be the sum of these exponents EI. So mu measures this ZP torsion part of the whole thing. And we define lambda to be the sum J equal 1 to L of dj times the degree of Fj. So lambda measures this ZP free part of the torsion part. So lambda will be equal to the ZP rank of this last sum here. And in the applications we have in mind, we will always take M to be A infinity for a ground field K that is finite to be an extension of Q. So I don't have a minus here anymore. So I take the projective limit of the whole P class group. And in this case, it is known that S is equal to 0. And the theorem of Ferrero and Washington implies that mu is equal to 0. So if I go back to my elementary module, I see that this lambda to the S disappears and this finite sum lambda over P to the EI disappears. So I'm left with this part, which is measured by small lambda. And the P rank and the ZP rank of A infinity are finite. because I don't have the lambda part, I don't have the mu part. And the ZP rank of A infinity will be equal to lambda, and the P rank will be equal to lambda plus the P rank of F, where F is the maximal finite submodule of A infinity. But now if I consider A infinity minus instead of A infinity, we have already seen in 2 slides back that F is equal to 0. So in this particular case, even the P rank of A and minus is equal to lambda for n large enough. And this has the following nice application. It's a theorem proved by me and Shamsuddin. So we let D be a positive square free integer such that D is congruent to 9 mod 16, and the biquadratic symbol 2 over P should be equal to 1, or D is the product of 2 different primes that are congruent to 3 mod 8. Then we define L and D to be the biquadratic field, or it's not biquadratic, it's the Galois group has rank 2, F Q adjoins square root of D, and mu 2 to the n plus 2. Then the 2-class group of L and D has the form z over 2 to the n plus r minus 2z times z over 2z, where 2 to the r is h2 of minus 2d. So this notation h2 means the 2 class number of the imaginary quadratic field q adjoint minus square root q adjoint square root of minus 2d. And we have a second theorem. If D is the product of 2 primes, P congruent to minus Q congruent to 5 mod 8, then the 2-class group of L and D is cyclic and is of the form z over 2 to the n plus r minus 2z, where this times 2 to the r is 2 times h2 of minus pq. And let me also say a little bit about the proof of this theorem. So in our very particular setting, L infinity D over L0 D is a cyclotomic ZP extension. And this cyclotomic ZP extension is totally ramified at all primes above 2. There's a formula due to Kida which allows you to compute lambda invariance explicitly. And this formula implies that lambda of A infinity minus is equal to 1. And one has to be a little bit careful here because Kida's formula is for classical plus and minus parts, or for classical minus parts. But it's pretty easy to show that the definition I just gave and the classical definition of minus 1 eigenspaces produce the same lambda invariance, so we can still use Kida's formula. Then there are some very beautiful results by Shamsuddin who show that the 2 rank of AN is equal to 2 in this setting. And we also can show that A of L and D plus, so of the maximal real subfield, is trivial in this setting. So if we know that the P rank is equal to 2, then there has to be a contribution of AN plus that does not come from the maximal real subfield. So it can only come from primes ramified in L and D over L and D plus. But these are naturally primes above 2. And it's easy to see that they have order equal to 2. So to obtain our final result, it remains to compute the growth of the ZP3 part, right? Because we have already taken care of everything that can be plausibly finite, and we are left with the A infinity minus part. So to do that, we look at the elementary lambda module associated to A infinity. But we have already seen that lambda of A minus is equal to 1, and that the plus part is uniformly bounded. So we can conclude that E, this elementary module, is isomorphic to ZP as a abelian group. So we can even assume that K2, which was this co-kernel, is trivial. And we define the polynomial nu n0 of t, which is t plus 1 to the p to the n minus 1 divided by t. And we can show that nu n0 times e is 2 times nu n minus 1 0 e for all n bigger or equal to 2. And by this, we obtain that e over nu n0 e is of size 2 to the n plus c for all n at least 1 and for some c. And the finite submodule of A infinity is annihilated by 2 and t. So in total, we get that an is 2 to the m plus d for n bigger or equal to 1 and some d. And now what we can do is for the case n equal to 1, we can compute the size explicitly. So we can determine d, and this gives the whole proof. And let me give some final remarks. So one of the main steps in the proof is to make Iwasawa's estimate that an is p to the lambda n plus nu for n large enough more explicit. So Iwasawa proves this for some abstract n large enough. In our very particular setting, where lambda is 1, we can make this explicit, and we get the formula for n bigger or equal to 1. And so far, it's not clear to us whether we can generalize these methods for settings with lambda bigger than 1 or rank greater than 2. Because if lambda is bigger than 1, then this assumption that K2 is trivial is not true anymore. So we are not sure how to handle this case. So we also have to somehow control the co-kernel, and these are very abstract, and I have no idea how to say anything about them. So far, we have also no idea how to handle the case when the class number of our real subfields are even. And if I understand it correctly, the rank estimates Shamsuddin gave are very particular for the case p equal to 2. So the precise methods do not work for p bigger or equal to 3. So this is one of the rare cases where we can prove something for p equal to 2, or we have no idea how to do it for bigger primes. And we can also use our results for L and D to obtain results on the nth layer of the cyclotomic 2 extension of the field K0D, which is just Q adjoint square root of minus D. And work in progress is to consider biquadratic base fields L0D, which do not contain the square root of minus 1. So if you go back to our joint theorems, you see that L and D always, if I put n equal to 0, I always get the square root of minus 1 in here. And the question is, can we weaken this assumption and put something else in here? And yeah, so far, I think the honest answer is we don't know yet whether it's going to work. And yeah, thank you very much for your attention, and I think I will stop here.
Thank you very much for this very interesting presentation. I would ask the participants if there is any question. Yes, if you have any question, you can open your microphone and tell it. Okay, let's start by some of my questions. I'm wondering whether you think, or you still think, that if the base field K does not contain the fourth root of unity, do you think that the minus part does not the projective limit of A minus, yes, the projective limit of A minus n does not contain a finite submodule? Do you think that's still true? Please reactivate your microphone, please.
I think you can definitely extend the result to that setting. Maybe you need another assumption, because the proof that there's no finite submodule depends on this capitulation freeness, right? So let me see whether I find that slide again.
Down.
So here. And I think you can weaken this assumption that mu2p has to be in K, but I'm not sure whether you might need some other assumption on the Hasse index in that case. I have to double check, but I'm sure that you can definitely extend this theorem at least a little bit.
And what if the class number of the plus part of the real maximal subfields equals 2? We could work on the case where the class number of the real maximal subfield is odd, but do you think that it is possible to make something if the class number is equals to, the two class number equals 2?
You mean if it stays constant equal to 2 along the whole real tower?
Yes.
It depends on the rank estimate. I mean, if you know that the rank is, if you are in a situation where the class number of the real field is 2 and the rank is 3, then it should still work. But if you only know that the class number is 2 and the rank is 2, then I think it gets more difficult because I'm not sure what's happening to the primes above 2. I'm not sure whether it could happen that the primes above 2 and the class group of the totally real field have some weird relation. One probably has to look at that more carefully.
Thank you very much.
It should be possible to find something. I would expect that in that very particular case, these ramified primes above 2 we had in our examples, that they just don't appear, that they are principal. And then the final result should look very similar to what we got so far.
Thank you very much. Are there any other questions? So thank you very much. I would like to thank all the lecturers of today, and we shall stop here. Thank you very much, Katharina Müller. Thank you very much, Azizul Haq. And the other participants can join the parallel sessions. They can find the links in the site, on the website of the conference. And we shall stop this Zoom meeting here. And thank you very much. Bye-bye.